Let's dive right into this explainer, the secret life of matter, the particle concert. You might be sitting in a totally quiet room right now. You're looking at a solid desk, maybe a still glass of water, and you're probably thinking that everything around you is just completely at rest. But honestly, the truth is, there is a literal, microscopic concert happening right under your nose, and it never, ever stops. So, what is absolutely everything made of? We have to start with this fundamental question. It's one that has haunted and fascinated curious minds for thousands of years. Because the seemingly still objects around you, your chair, your coffee mug, the literal air you're breathing, are actually full of this hidden, relentless movement. Everything is made up of incredibly tiny pieces, and they are basically throwing a wild, energetic party 24/7. To understand how we actually figured this all out, we have to look back. We start in the 1700s with early theories from folks like Democritus, moving into the 1800s when Antoine Lavoisier really gave chemistry its rigorous edge. But the true mind-blowing moment, that happened in the early 1900s. Albert Einstein finally proved atomic theory. And he did it by mathematically explaining how tiny particles, like pollen, were jittering and moving completely randomly in water. He realized, wait a minute, invisible water particles are constantly crashing into this pollen. The invisible world was finally brought into the light. Now, scientists use models to explain phenomena that cannot be easily seen. Because we can't easily just look at these tiny particles, even with our most powerful microscopes, we have to rely on scientific models to wrap our heads around them. So to really grasp how matter behaves at that microscopic level today, we're going to use a highly relatable model, a concert. By imagining these invisible particles as energetic fans at a live show, this whole secret life of matter is going to make perfect intuitive sense. Which brings us to kinetic particle theory, a scientific idea stating particles are always moving, and their speed depends on their state of matter. Think of this as the ultimate rulebook for our concert. It tells us that particles are always moving, always, even if you're looking at a freezing block of solid ice. And the absolute most important part of this, the speed of their movement depends entirely on their state of matter. Basically, the more energy our concert fans have, the more active they get, and the more the behavior of the whole crowd shifts. Let's compare a solid, which has a definite shape and volume, with a gas, which has an indefinite shape and volume. Before we zoom into the really granular details, let's look at the two extreme ends of the spectrum. On one hand, we've got the incredibly rigid, strict rules of solids. On the other hand, we have the total freedom and chaos of gases. It is literally the difference between being strapped tightly into a roller coaster seat versus free-falling through the sky. Let's start with solids. Think of solids as our front row VIP section at this concert. Because they have a definite shape and volume, they just maintain their size and occupy a fixed amount of space unless some major outside force acts on them, like someone pushing aggressively through the barricade. Otherwise, they are incredibly stable. When you look at the microscopic level, you can see exactly why solids behave this way. These particles are tightly packed together in a highly regular pattern. They have incredibly strong attractive forces between them. It acts a whole lot like linked arms, keeping everyone locked firmly right in their fixed front row positions. Now, they vibrate, they're definitely bobbing their heads to the music, but they aren't actually going anywhere. Okay, let's move on to the particles of liquids. If solids are that locked-in front row, liquids represent the mingling crowd heading out to the concession stands. They're still at the concert, for sure, but the vibe has completely changed. They are flowing, they're walking around, and they're sliding past one another to grab a drink. The crucial point here is how they balance two things, high density and flowability. Liquids have a relatively high density compared to gases because all those particles are still quite concentrated in a specific volume. But unlike our rigid front row, they have flowability. This means liquid particles are mobile enough to flow and be poured, just smoothly sliding and moving past each other in the crowd. In liquids, you can see the particles are still closely packed, but they completely lack that perfect, regular pattern we saw over in the solids. Why is that? Well, because the attraction forces between them, while still stronger than in gases, are definitely weaker than in solids. The arms are unlinked. People are still bumping shoulders in the crowd, but they have the freedom to shift around and weave through the group. And what exactly gives them that ability to weave through the crowd? Kinetic energy. Kinetic energy allows movement. The liquid particles simply have more kinetic energy than solid particles do. Just that little boost of extra energy gives them the mobility to break those rigid bonds and slide past each other while still remaining relatively close together inside the venue. Next up, we hit the absolute extreme end of the spectrum, gases. Gases have an indefinite shape and an indefinite volume. If solids are the front row and liquids are the concession crowd, gases act exactly like the fans sprinting away into the open parking lot after the show ends. They are just bursting with kinetic energy, and they completely lose any cohesive shape or fixed volume. Just notice how incredibly spread out the gas particles are here. Because they have so much kinetic energy and virtually zero attractive forces holding them back, they are completely free to move. A gas is going to fiercely expand to fill whatever space is available to it, regardless of how big the container is. Seriously, if you open a bottle of perfume in a room, those particles are sprinting to every single corner of that room as fast as they physically can. So let's check out the characteristics of a physical change. We have a change in size or shape, a change in state, a change in color or appearance, and crucially, no new substances formed. Now that we know how our concert fans behave at all these different energy levels, let's talk about what happens when matter actually transforms. When matter goes through a physical change, say moving from a solid to a liquid, we might see a change in size or shape or appearance, but no new substances are formed. Melting an ice cube just changes the concert venue from a solid block to a liquid puddle. But the fans themselves, the water molecules, they remain exactly the same. So, physical changes can often be reversed without changing chemical composition. And because the actual substance hasn't changed at all, physical changes can usually be reversed just by shifting the conditions. If you melt that ice cube, you can literally just put it right back in the freezer to reverse it. But contrast this with a chemical change. A chemical change means you're creating an entirely new substance. Going back to our metaphor, a physical change is just the crowd moving to a new stage. A chemical change is firing the musicians and creating an entirely new band. Let's do a quick check. Is shredding a physical change? Think about something like shredding a piece of paper. You're violently tearing it to pieces, completely altering its original form. But ask yourself, did you create a completely new substance? No, it's still just paper, right? Just in tiny pieces. You only changed its size and shape. Therefore, it is strictly a physical change. How about this one? Which of the following is a chemical change? Dissolving sugar, breaking glass, fermenting grapes, or boiling water? When you look at these everyday processes, only one of them actually transforms the chemical composition. Think about it. Dissolving sugar just hides it in the water. Breaking glass is just a change in shape. And boiling water, that's just a change in state from a liquid to a gas. But fermentation, that process chemically alters the sugars in the grapes to create alcohol. Boom, you have formed a brand new band. Finally, when a substance undergoes a physical change, which of the following remains unchanged? The state of matter, color, or the chemical properties? As we wrap up this explainer, consider this. When our concert fans shift from that locked-in front row to sprinting out the exit, their fundamental identity is preserved. The state of matter changes, sure, but the chemical properties do not. The substance itself remains completely unchanged. So the next time you look at a melting ice cube, a boiling pot of water, or even just that seemingly still desk right in front of you, remember, you aren't just looking at inanimate objects. You're looking at a never-ending, hyperactive kinetic party.